In this example, we want to look at constant acceleration in one dimension. So looking out your window, you see a ball pass right by your window going up. Your window is 1 meter tall and the ball is visible for only a quarter second. How long will it be before the ball is visible again? Well, what to do with this one? Well, let's start with a picture. So I have this window and I know that it's 1 meter tall. So I see this ball, and this ball is going up, but I only see it for a quarter second before it leaves the window frame. Well, then what happens? Well, presumably, the ball is going to go up further until it reaches some maximum height, and then come back down. Now I've offset the path here a little bit so I can see it, but it's all in one dimension, so it comes right back down on top of itself. Eventually, it gets to the upper edge of the window again, and then reappears. So when the question asks how long will it be before the ball is visible again, it means precisely the amount of time that the ball spends above the upper edge of the window. So how to find that? I've started with a coordinate system with the base at the bottom of the window with positive x pointing up. What physics applies to this problem? Well, obviously the constant acceleration physics applies to this. It's in free fall. The acceleration is just that due to gravity. To apply the constant acceleration relationships, I need to choose 2 points in time. Which 2 points should I choose? Well, one obvious choice would be the time that it leaves the window and the time that it gets back, because that time difference is precisely the time that I'm looking for. But I'm not going to start there, and I'll tell you why. I don't know a lot about what happens up there. It's outside my view. I also don't know what happened below the window. I don't know how far I am above the ground. I don't know how it was launched. I don't know any of those things. Where I know information is in this region, the region when the ball is crossing the window. And so I'm going to choose as my initial and final time, the initial time when it first appears at the bottom of the window, and the final time to be the time that it leaves. Now, if you have chosen the 2 points in time up here first, that's not wrong. But you'd have to come back to these 2 points of time eventually. And I chose that because that's where I knew information. And I want to start from where I know things. Okay, so what are those times? I'm going to set my initial time equal to 0, and the final time I know to be a quarter second. So the time difference is also just a quarter second. Do I know the initial and final positions? Yes, I know that as well. The initial position is 0 given this coordinate system, which makes the final position to be a positive 1 meter. What about the velocities? That's where I don't know anything. I don't know the initial or final velocity in this case. I do know the acceleration, of course. The acceleration due to gravity is a negative g given this coordinate system where positive is up. So what relationships can I apply to this problem? I don't know either velocity, which means any equation that has both velocities in them, I'm not going to be able to solve directly. But you know, there is that one equation that only has the initial velocity. The one where you have the final position is equal to the initial position plus the initial velocity times the time interval, plus 1/2 the acceleration times the time interval squared. Do I know it? I know the final initial position. I know the acceleration and time interval. I know everything except the initial velocity, so I can use this equation to find that initial velocity right away. So plugging in the numbers, I have a final position of 1 and initial position of 0. The time is 1/4, and then 1/2 acceleration negative g times the time squared, which is 1/4 squared, which is 1/16. Bringing the g over 32 to the other side, it becomes positive. And now if I multiply by 4, I get the initial velocity is 4 plus g over 8. So I plug in numbers at this point and find the initial velocity is 5.225 meters per second. I'm keeping all 4 here so I don't have rounding errors in my internal calculations. So I have the initial velocity. Can I find the final velocity? Sure, almost anything will give us that. Probably the easiest relationship is the one where the final velocity is just equal to the initial velocity plus the acceleration times the time interval. Putting in numbers to that, the initial velocity and the acceleration and the time interval, which is 1/4, I can calculate now the final velocity, which is 2.775 meters per second. So this is all part of the brainstorming stage. I have this problem, I know what I want to find, I don't know how to get there, but I know where I have information, which is this time interval between when the ball entered the view and when the ball exited the view, and I used that to accumulate more information, the initial velocity when it came into the window and the final velocity when it left. And don't you think that's going to be the important one? Now that I know velocity when it leaves, I know more information about what's going on after it leaves the window. And I think if I look at that area now, we should be able to come up with the right answer. So let's do it. I brought the picture back, and now I want to choose 2 points in time and establish a coordinate system. I've started a new coordinate system this time. You could use the old one, there's nothing wrong with that. Since I have the freedom to start from scratch, I'm going to do it. I set the 0 at the top of the window this time and positive x up. And the 2 points in time I'm interested in is the point that it leaves the top of the window and the time that it comes back. So what are those times? Since I'm starting fresh, I set the initial time equal to 0, the final time equal to capital T, which means the time interval is this capital T, and that's what I'm looking for. Once I have that, I'm done. What about the initial and final position? Well, given this coordinate system, the initial and final position are just both 0. Let me take a minute to point that out. A lot of students want to start with the equations, they have all of these parameters and they're trying to figure out what they are. But with a very clear picture, and once you establish your coordinate system, a lot of times you just look at your system and choice of coordinate system and you can just write the answers down. Given the 2 points in time that we're interested in, the location of the object at both the initial and final time is 0. What about the velocities? Well, the initial velocity we know, it's 2.557 meters per second, and it's pointing up, so it's positive. We don't know the final velocity, or do we? We do, in fact. It's negative 2.775, and that's exclamation point is for excitement, it's not factorial. It has to have the same magnitude, but pointing in the opposite direction. And you might ask, well, can I prove that, or am I just guessing because it's symmetrical? Well, it is symmetrical, and I'm not guessing. If you look at the velocity graph, in constant acceleration, we know that it's a straight line. And the point where it goes through 0, that's the point at the top where it goes to rest. Because it's a line, it's symmetrical on either side of this point. And so if you go at equal times or equal distances on either side, you're going to get a magnitude of the velocity that is the same, except it's pointing in the opposite direction. So from the symmetry of the problem and our graphical understanding of the velocity, we know that the velocity has to be the same, just pointing in the opposite direction. Again, we know the acceleration is negative g. Well, we know everything about this problem now except the time interval, so I just grabbed probably the simplest relationship where the final velocity is equal to the initial velocity plus the acceleration times time. If I put in those values of the velocity and the acceleration, I get this. And now I'm going to bring that 2.775 to the other side, where we have a negative twice that then, and then divide both sides by negative g. The negatives cancel, and now I can plug that into my calculator, and I get the time interval to be 0.556 seconds. Is that reasonable? In a quarter second, as it passed through my window, it lost almost half its velocity. It went from 5.225 to about 2.775. So not exactly half, but it lost nearly half its velocity in a quarter second. So then, if it goes completely to rest and then comes back in about half a second, that seems about right. So we have some confidence that we have the right answer.